Welcome to how to use a double integral to find the moment of inertia for a circular disk. We will be setting up this double integral in polar coordinates. We will consider a rotating circular disk of mass m and radius r. We will assume that this disk has a uniform mass density ρ, perhaps measured in grams per square centimeter. Let's talk about the moment of inertia I of a solid body. If a mass is rotating about the axis A with angular speed omega, and the resulting rotational kinetic energy is k sub r, and here's a picture of what we have. Here's our disk in this case, that's our solid body. It's a lamina, it's flat, has some mass, and it's rotating about this axis. We can define the moment of inertia I about that axis by this equation, k sub r, kinetic energy, equals 1/2 I omega squared. So there's a relationship between the kinetic energy of rotation and the angular speed omega and the moment of inertia I. We could solve this for I, which is what we're going to do later when we work out the example with this rotating disk. So the question then is, what is omega? What do we mean by the angular speed? So let's ask, what is angular speed omega? Suppose we have a point mass m, shown here, revolving about an axis which we'll call A. So it's going around and around here in a circular orbit. And let's suppose that the mass m makes one complete revolution all the way around. In other words, 2 pi radians, going around in 2 pi radians, in an amount of time t seconds. We will then have a periodic motion with period t seconds. But we can also say that its angular speed is given by omega equals 2 pi over t. You go through 2 pi radians in t seconds, so the angular speed measured in radians per second would be 2 pi over t. This could be measured, for example, omega could be measured in radians per second. The angular momentum I just depends on the geometry of the solid and the chosen axis of rotation. In our particular case, we have a disk, circular disk of radius r and mass m, rotating about its axis of symmetry. Let's talk about the units of measure for this moment of inertia I. First of all, we have the kinetic energy of rotation is 1/2 I omega squared. So we know that the kinetic energy has the same units as 1/2 mv squared, or mv squared itself, which is mass times velocity squared. Velocity is distance over time, divided by time, so we get mass times the distance over time squared. We know that omega is equal to 2 pi over t, and so omega has units 1 over time. This numerator is in radians, which really has no units associated with it. Time could be measured, for instance, in seconds. So we could have omega measured in, for instance, 1 over a second. So then the moment of inertia, I, which is equal to, by this equation up here, the kinetic energy divided by 1/2 omega squared, is what? What units does it have? We saw that the kinetic energy has these units. Omega squared has units 1 over time squared. And we notice we have a 1 over time here squared. We also have a 1 over time here squared too, since time is in this denominator. So this whole fraction simplifies to mass times distance squared. For instance, we could measure the moment of inertia I in kilograms. That's a good unit for mass. times meter squared, which is a good unit for distance squared. Let's talk about the kinetic energy of a point mass due to its revolution around an axis, the kinetic energy of rotation. So we have a mass here, it's revolving around this axis, and it has a circular orbit, and the angular speed is omega. Let's say that this mass is m, and the circle has radius r. In that case, as I just said, we're going to have a point mass m revolving around an axis at a distance r, and let's suppose it has constant angular speed omega, measured perhaps in radians per second. In that case, in t seconds, the distance that the mass m travels going around the circle, maybe a fraction of one time or many times, is the distance equals omega times r times t. So the instantaneous speed of the mass then, v, which is measured in distance traveled divided by time, the distance is going to be r omega t, which we had up here, divided by time t, and that simplifies to r omega. So the kinetic energy then of this mass at that instant of time is 1/2 mv squared. So we can write the kinetic energy of rotation is 1/2 m, and then v squared is r omega quantity squared. The velocity, remember, was r omega. This can be simplified just a little bit using laws of exponents to get 1/2 m r squared omega squared. Let's look at an example of the kinetic energy of rotation of a point mass. Let's suppose we have a mass of 2 kilograms and it's revolving 3 meters from its axis of rotation at 5 times per second. In that case, omega is going to be 10 pi radians per second. You're going around 5 times, which is 5 times 2 pi radians. So omega equals 10 pi radians per second. In that case, the kinetic energy using our formula 1/2 m r squared omega squared is going to be 1/2. The mass is 2 kilograms, r is 3 meters, and omega is 10 pi per second, and we have squareds in all the right places. So then, if we simplify that, what we get is 900 pi square kilogram times meter squared divided by second squared. And if we look at that, we notice that on this side we basically have mv squared in the metric system. Kilograms times meters per second quantity squared is measured in joules. And so this tells us that we have 900 pi squared joules of kinetic energy for this 2 kilogram mass rotating at 5 times per second, 3 meters from its axis of rotation. So, in our circular disk problem, how will we proceed? To find the kinetic energy of rotation of a disk rotating about its axis of symmetry with angular velocity omega, we will partition that disk into a finite number of subregions. We'll break it up into little pieces, and then for each subregion, we will find the volume of that subregion, and since we know the mass density, we can find the mass of that subregion. Remember, we're assuming that the mass density rho is constant. Find the distance r from that subregion to the axis of rotation, and then if the disk is rotating with an angular velocity omega, find the rotational kinetic energy of just that little piece. Add up the kinetic energies of rotation for all those small pieces, those small subregions, to approximate the total kinetic energy of the rotating disk. That sum of the kinetic energies of rotation for all the little pieces of the circular disk we can interpret to be a Riemann sum for a double integral. Once we have computed the total kinetic energy of rotation k sub r using double integrals, which we'll see later, we can find the moment of inertia I of the disk, and we can do that by using the formula: the kinetic energy of rotation is 1/2 I omega squared. So the process is to first use a Riemann sum to approximate the kinetic energy k sub r, then take the limit to change that into a double integral, and we will evaluate a double integral to calculate the kinetic energy exactly. For a double integral over a circular disk, to calculate the total kinetic energy of rotation, we will use an integral, a double integral, in polar coordinates. We're not going to extensively review polar coordinates. Hopefully you've seen them before. And here's the idea. At 0, 0, we have this point, and we have an axis, positive ray coming out like this, which corresponds to theta equals 0. From this, as our basis line, we draw angles coming out like this. Theta equals pi over 8, pi over 4, 3 pi over 8, pi over 2, and so forth. We can have positive or negative values of theta. Theta can also be larger than 2 pi. We also are going to have, for this graph paper, concentric circles. This last circle here, if you look at what we have for the number line down here, our x and y axes, this circle on the outside is r equals 3. If you look at this circle right here, it's r equals 2. This one is r equals 1. Right at the origin, r equals 0. Let's look at a region in polar coordinates. Let's look at this small bluish region here. Suppose the two circles that are shown here, and they are concentric circles with center at the origin or pole of the polar coordinate system. Let's let this inner one be r, the radius equals r sub j minus 1. This next one, r equals r sub j. Let's also have two rays coming out. Theta equals theta sub k minus 1 for this ray, and theta equals theta sub k for that ray. And then a sub jk, this region in here, is in polar coordinates the set of all points having polar coordinates r, theta, where r is between r sub j minus 1 and r sub j, and theta is between theta sub k minus 1 and theta sub k. We have two rays here. Personally, I think I only know one ray. But in any case, we'll let delta a sub jk be the area of this region a sub jk. So a sub jk by itself is a planar two-dimensional region. Delta a sub jk is going to be the area of that subregion. So let's look at that area element in polar coordinates more carefully to see what the area of that subregion is. So here's the picture that we saw on the previous slide. A sub jk is this region right in here. So the area of a sub jk can be computed the following way. We can compute the area of this ring between those two concentric circles, and that will give us the area of this whole thing. And then, because we have two boundaries here, theta equals theta sub k minus 1 and theta equals theta sub k, we're only getting for this region here a fraction of this total region. So delta a sub jk is the area of that ring times the fraction of the ring given by the theta sub j's. So here's what we have. the area of the ring is going to be the area inside this outer circle, which is pi r sub j squared, minus the area of this inner circle, which is pi r sub j minus 1 squared. So the area of the ring is given by this stuff right here. The fraction of the ring area that is right in here is just the difference of the thetas, theta sub k minus theta sub k minus 1, divided by 2 pi radians, which would be what you get going all the way around. Okay, now we can simplify this. We can write this difference of squares, r sub j squared minus r sub j minus 1 squared, as sum of r sub j and r sub j minus 1 times the difference of r sub j and r sub j minus 1. And then the rest of the stuff is the same as what we have up here. And then let's just do a little bit of rearranging. Here we have a pi. Here we have a pi also. And so I'm going to take this pi divided this pi, and here it is right here. Next thing I'm going to do is worry about this denominator factor of 2. I'm going to associate it with this factor and rewrite it as r sub j plus r sub j minus 1 divided by 2. This factor stays the same as it was before. We've moved away the 2 pi in the denominator, so from this we only get the difference of the thetas. So now we look at this, and what do we see? Pi over pi is 1, that's okay. Let's look at this next factor. This is the average of r sub j and r sub j minus 1. Let's call this average r sub j star. R sub j star would be halfway between r sub j and r sub j minus 1, right about here. Then we have the difference of the r sub j and r sub j minus 1, and then the difference of the thetas. So let's write this factor as r sub j star. Let's write this one as delta r sub j. Let's write this factor as delta theta sub k. And so if we let things shrink down towards 0 for the lengths of each side, we get a differential, an equation involving differentials. dA is going to be r dr d theta. And this is what we're going to use when we integrate in polar coordinates. We will have a double integral of something times dA, and we'll use this to change it to an iterated integral, an integral of an integral. So let's look at the kinetic energy of just one small piece of this disk as the disk rotates. So we'll assume that the disk has radius r and a mass density rho, and its mass of the total disk then is the area of that circular disk times rho, so that's pi r squared times rho. And then if we let that little subregion here go around and around, here's what we can say. The little subregion that we talked about, let delta m sub jk be the mass of this little piece a sub jk. So let's see if we can calculate the kinetic energy that this little subregion has, its mass going around a circle from its axis of symmetry, which in this case is coming out of the slide towards you. So the kinetic energy, which I'll call K sub jk, is going to be 1/2 the mass of that little piece, m sub jk, times the velocity it has, which is going to be r sub j squared times omega squared. Now, the mass here, m sub jk, can be written as rho times the area, delta a sub jk, and then the rest of this is the same as before. We still have the half here, half here. We still have the r sub j squared in both of these as factors. We also have omega squared as factors. So the jkth kinetic energy is given by this. So if we add up the kinetic energies from all the little pieces of that disk, we're going to get that the kinetic energy of rotation is approximately 1/2 the sum over J and K, the mass of the jkth subelement of the disk, times r sub j squared times omega squared. But remember that delta m sub jk can be written as rho times delta A sub jk. So plugging that in, this stuff equals this stuff. And so the total disk kinetic energy then is going to be what? Well, let's just look at this a little bit further. We have a factor of rho, which is right here. We have delta A sub jk, the area of that jkth element, which is r sub j star times delta r sub j times delta theta sub k. And then we have r sub j squared as a factor and omega squared as a factor. So we have that the total disk kinetic energy of rotation is 1/2 the sum over J and K of rho times r sub j star times delta r sub j times delta theta sub k times r sub j squared times omega squared. Let's take the limit of Riemann sums that look like this as the number of subregions goes to infinity and the dimensions of each subregion go towards 0. In that case, the total disk energy, kinetic energy of rotation, instead of being approximately equal, is actually going to equal 1/2 the limit as the norm of the partitions goes to 0 of the stuff that we have up there. This just says that in the limit, we're doing what we said here. All the dimensions of the subelements tend to 0 in the limit. Well, this is a Riemann sum for a double integral. And the double integral is this one. The total disk kinetic energy of rotation is 1/2 the integral from theta equals 0 to 2 pi, r equals 0 to capital R, of what we have here. We have an r squared right here, omega squared right here, rho the mass density here, and we also have r dr d theta over here. Okay, we can rearrange these things just slightly and say that the total disk kinetic energy is equal to this. All we did was move the factor of rho out front, no big deal. R squared times r is r cubed, and then we also have dr d theta, and we also moved omega squared outside this iterated integral since omega squared does not depend on theta nor lowercase r. So far we have the total kinetic energy of rotation for this rotating circular disk is 1/2 times this integral times omega squared. Let's see what we can do with that. First of all, here we're integrating with respect to r, this stuff dr. Rho is a constant. An antiderivative of r cubed is 1/4 r to the 4th. So let's use the fundamental theorem of calculus. This inside integral, the integral with respect to r, is just going to be 1/4 r to the 4th. That's the antiderivative of this, evaluated at r equals 0 and capital R, and subtracted. And the rest of the terms just came along for the ride. Rho is a constant, omega squared is a constant, and so this stuff we will eventually be integrating with respect to theta. So let's see what we can get here. If we look at this factor right here, that's just 1/4 r, capital R to the 4th minus 1/4 0 to the 4th. So that gives us 1/4 capital R to the 4th. We also get these constant factors, and integrating theta go from 0 to 2 pi of all of this stuff, which is basically a constant as far as the variable theta is concerned, gives us this factor of 2 pi. So we get 1/2 and then this integral gives us the factor of 2 pi, and then we have this stuff here. And so the total disk kinetic energy is equal to this. It's in terms of, let's see, the angular speed, omega, the mass density, rho, and also the radius of that rotating disk. So now we can rewrite that because we have a 1/2 times 2 times a fourth here. That just gives us a fourth. So the total disk kinetic energy of rotation can be written this way. But then let's think if we can simplify this somehow. The mass of the disk is the area of the disk times the mass density, mass per unit area. And if we use this relationship up here, we can write that kinetic energy of rotation in the following way. The total disk energy of rotation is 1/4 omega squared times m times r squared. We can see how that happened, can't we? We have a pi here. We have an r squared that we can take out of this r to the fourth. And we also have a factor of rho here. And so all three of these factors do appear up here. So take those out, call the product of them m, and we get 1/4 omega squared m times r squared. So we have that the kinetic energy of rotation of that disk is 1/4 omega squared times the mass m times the radius r squared. But we also have by our definition of I, the moment of inertia, that the kinetic energy of rotation is 1/2 I omega squared. If we look at those two equations, both of these are expressions for the same kinetic energy, so these have to be equal, and we can solve those two equations for I. So if we do that, we can first set this equal to this, which is what we have here. We notice that this side of the equation has a factor of omega squared, so does this side. So divide both sides of this equation by omega squared, and we have 1/4 mr squared equals 1/2 I. Now, if we multiply both sides of this equation by 2, we can easily solve for I, and what we have is that I equals 1/2 mr squared. So this is the formula for the moment of inertia of a circular disk having mass m and having radius r. So, what have we done? We broke up the circular disk into small pieces rotating about the axis of symmetry. We approximated the kinetic energy of each piece revolving around the axis, whatever angular speed it has, and found the sum of those kinetic energies that approximates the total kinetic energy of the disk. We interpreted this sum as a Riemann sum for a double integral over the disk. We evaluated that integral and found that the total disk rotational kinetic energy was 1/4 omega squared times the mass times the radius squared. But we also had, by our definition of I, that the total disk rotational kinetic energy was 1/2 I omega squared. Solving these two equations for I, we found that I equals 1/2 mr squared. So this was our formula for computing the rotational inertia of the circular disk, the moment of inertia of that circular disk. Thank you for watching this video. This video involved a two-dimensional problem involving the moment of inertia I for a circular disk. A circular disk in, let's say, the XY plane that's rotating about the z-axis. Please watch for future videos. The next one coming up, I suspect, is going to involve the moment of inertia for a three-dimensional solid, which is a cone. This problem will involve triple integrals, and we will hopefully look at it in both cylindrical coordinates and in spherical coordinates. Have a nice day.